which experiment my group will be doing today. The final experiment, experiment number 2, which is the batch liquid reactor. Now, the heart of any chemical process is the reactor. Generally, there are 3 types of reactors, namely a batch reactor, a continuously stirred tank reactor, which is also known as CSTR for short, and a plug flow reactor, also known as PFR. In a reactor, reactants undergo chemical reactions to form the final desired product. A batch reactor is one in which all the reactants are loaded in at once. The conversion of the material in the reactor varies with time. However, at any one time, the conversion is uniform throughout the reactor. A stirrer is usually used as an agitator to mix separate feeds and enhance the heat transfer. A batch reactor is used in chemical processes for small-scale production, for the testing of new processes that have not been fully developed yet, and also for the manufacture of expensive products. The main advantage of a batch reactor is that we can obtain a high conversion. This is usually done by leaving the reactant in the reactor for a longer period of time. However, the batch reactor also has its disadvantages. First, it has a high labor cost per batch production. Besides that, it is also not feasible for large-scale production. In our experiment, we will be using ethyl acetate and sodium hydroxide solutions in a semi-batch reactor, while using different speeds of stirrer to agitate the reaction. There are 2 objectives in our experiment. The first is to prepare a calibration curve of conversion versus conductivity for ethyl acetate and sodium hydroxide solutions at different concentrations. Second is to study the effect of different speeds of stirrer on the batch saponification of ethyl acetate and sodium hydroxide. Now, let's go into the lab so that we can get started with our experiment.
Hello everyone, so let's start our experiment. Follow me. So, in our experiment, we use 2 different types of solution. The first one is sodium hydroxide and second is ethyl acetate solution. So, as you can see here, this is the different type of solution which is ranging from 0.025 molarity until 0.075 molarity for each solution. So, next, let's move on to the apparatus setup. So, as we can see, here is the apparatus that is being set up to conduct our experiment. So, the first and foremost important instrument that is being used in this experiment is the reactor itself. So, as we can see, this reactor is a batch type reactor. And after that, we have the control panel, which consists of many electrical instruments that is being used to measure different types of parameters in our experiment. And last but not least is the DAS, also known as Data Acquisition System. So, in this DAS, we are going to mark our data that is going to use for the experiment. So, for our experiment, there are 2 parts, which is part A and part B. So, for our first part, it is the preparation for the calibration curve, and the second part is to study the batch saponification reaction in this experiment. So, for our first part, we're going to use different types of molarity for our solution. So, let's take a look at the preparation of the solution. Here is the different molarity for our solution, and we're going to use different for each steps. So for example, first we take 0.05 molarity of sodium hydroxide, and then we're going to pour it into our reactor. So here is our reactor, and then we're going to pour the solution inside of it, and after that we're going to set the stirrer, the speed of the stirrer at about 200 RPM, also known as rotation per minute. And after that, we quickly click the start button in our DAS system in order to get the conductivity value. So after we click the start button, the system will take the data of the conductivity for interval of 1 minute and for 30 minutes. So moving on to the second part of our experiment. So first, we prepare the solution, and after that, we pour all the solution inside our reactor, and then we set the stirrer speed at 50 RPM, and once we start the stirrer speed, we quickly click the start button in our DAS system in order for the system to collect our conductivity data, which is at 1 minute interval for 30 minutes period. And after that, once we finish collect the data, we open the valve in order to empty our reactor, and then we use different speed of our stirrer, ranging from which is 100, 150 and 200 RPM. So after that, we just repeat the procedure, and then our experiment is finished.
Hi, now I'll continue with the calculation part. After we obtain the calibration curve from the 5 solutions, we're going to input the y-axis, the intercept and also the gradient value into the computer system. After that, the experiment will be run with different concentrations of the different agitation levels, and the conductivity and conversion values will be recorded. And all of these will be tabulated inside a table, which is until the 30th minute mark. Now, before we determine the zero order, first order and second order of the reaction, we have to go through some basic derivations to know what is the y and also the m of the equations. Firstly, we must have the mole balance of the batch reactor, which is equates to Na0 dx over dt equals to negative RAV. The rate law, which is negative K, and also the stoichiometry coefficient, which is Ca equals to Ca0 1 minus x. After combining all of this, we will get a combined equation, which is dx equals to K over Ca0 dt for the zeroth order reaction. From here, we integrate the whole equation to get x equals to K over Ca0 t, where x is the y of the graph and K over Ca0 is the m, the gradient. Now, moving on to the first order equation, the only difference is the rate law, which is negative Ra equals to Kca. After this, we will again combine the mole balance, rate law and stoichiometry coefficient to form an equation dx over dt equals to K bracket 1 minus x. After integration, we will get an equation negative ln in the bracket 1 minus x equals to kt, where the negative ln 1 minus x is y and the k is the gradient of the graph. Now, moving on to the second order reaction, again the mole balance and also the stoichiometry equation will be the same, but the rate law will be negative Ra equals to Kca squared. By combining all of this, we'll get a combined equation of dx over dt equals to Kca0 bracket 1 minus x squared. By integrating this equation, we get x over 1 minus x equals to Kca0 t, where x over 1 minus x is the y and Kca0 is the gradient of the graph. Now, after we determine all of these equations, we sub the conversion value into these equations. Then we plot the graphs. which is the graph of zeroth order, which is plot against x equals to x against t. Now for the figure 2, the graph is plot of negative ln minus x against t. For the second order graph, which is in figure 3, x over 1 minus x is plot against t. After we determine the order of the reaction, we would like to know the rate law of our reaction. This is obtained through the gradient of the graph. For example, at 50 rpm, our reaction is at second order, and the value of the gradient is at 5.736. By using the gradient, we equate this to kCa0 and get a K, the rate law, of 0.5736 over molar second. This method is used throughout the experiment to obtain the rate laws for the other agitation levels of the batch reaction.
So now let's do some discussion on the results that we have obtained. So from the methodology part, in part A, we have used two types of solution, which is sodium hydroxide and also ethyl acetate with different range of molarities ranging from 0.025 molarity to 0.075 molarity. With these two solutions, we are able to determine its conductivity value and also its conversion. From the graph given, we obtain the equation of y equals to negative 0.0931x plus 1.8989. Here, we obtain that the gradient is negative. When the conductivity value decreases, the conversion will increase. This can be simply explained by the concentration of hydroxide ion present in the solution. When there is no reaction occurring, the hydroxide ion is available and present in large amount, which is measured by the conductivity. When reaction is occurring, these hydroxide ions will react to form compounds or even products, which leads to the decreased amount of hydroxide ion, which then leads to the decreased amount of conductivity. This part of experiment, we are going to use the calibration curve from the previous part of the experiment to determine the conversion between sodium hydroxide and also ethyl acetate. In this part of experiment, we are going to use stirrer speeds ranging from 50 rpm to 200 rpm. The objective of the experiment is actually to determine the rate law of the reaction by using a method called integral method that had been explained by Hao Yang before. To determine the rate of reaction, we can just compare between three graphs, which is figure 1, figure 2 and also figure 3. So for 50 rpm at zero order, the R squared value is at 0.6873. For the first order, the R squared value is at 0.945, while for the second order is at 0.9877. This R squared value indicates the compatibility between the data. Therefore, we can say that at 50 rpm, the reaction is at second order reaction. So next will be the 100 rpm. For the 100 rpm stirrer speed at second order of reaction, the R squared value is at 0.8596. For the first order will be 0.7936, followed by the zero order at 0.714. Same trend can also be observed in 150 rpm and also 200 rpm with the R squared value of 0.796 and also 0.6283 respectively at the second order. Theoretically, a stirrer is introduced to provide agitation to the reaction for the reaction to occur faster. With higher stirrer speed, the faster the reaction occurs. Based on figure 3, 50 rpm stirrer speed gives the highest value of R squared. Our data indicates that the fastest reaction occurs at 50 rpm rather than 200 rpm, which contradicts with the theory. The contradiction may occur because the solution that we have used may be too diluted, which thus affects the conversion value in a significant amount. Therefore, we are safe to say that all of our reactions that we have conducted in this experiment followed the second order of reaction. The rate constant that we have obtained for 50 rpm is 5.736 per molar per second. For 100 rpm is at 0.602 per molar per second. For 150 rpm is at 0.336 per molar per second. And last, at 200 rpm is at 0.102 per molar per second.
Okay, to conclude, in our experiment, we used ethyl acetate and sodium hydroxide solution in a semi-batch reactor while applying different speeds of the stirrer to agitate the reaction. For the first part of the experiment, which is the calibration of the conversion versus conductivity of ethyl acetate and sodium hydroxide at different concentrations, a negative gradient was obtained. This is because the conductivity decreases, or in other words, the hydroxide ion decreases as conversion increases. In the second part of the experiment, we found that the usage of 50 rpm of the stirrer speed yields a faster reaction compared to the 200 rpm stirrer speed. This, however, contradicts with the theory because in theory, the faster the stirrer speed, the faster the reaction will take place. In conclusion, for the batch saponification of ethyl acetate and sodium hydroxide, a stirrer speed of 50 rpm in a second order reaction is optimum. Now that we have come to an end for our experiment, we'd like to say thank you and bye-bye!